what happens when you have a bar, like the one I've drawn here, with two different materials that are welded together, and they have to deform the same axially? What happens when that bar has a change in temperature, and let's say it's uniform change in temperature on both materials, although we know that, if you have an ambient temperature, it'll start to have its effect inward into this, and material 1 will probably heat up first than material 2, but given enough time, these two will have a constant temperature, and they will want to deform. But what happens if material 2 has a larger thermal expansion coefficient in comparison with material 1? Well, if they were unrestrained and unwelded, material 2 would want to deform more than material 1. And so that constitutes a case of incompatible displacements, because we already said on the onset that they are welded and they have to deform the same. So what happens is that this creates a incompatibility that has to be resolved by the means of internal stresses. So the material 2 will have a compression force, and the material 1 will exhibit a tension force that will eventually equal out the difference that would have occurred if the two materials were not welded together. Basically, if we want to write that in the form of an equation, this is what it would look like. So we're basically saying that the final deformation on the two materials has to be exactly the same. So that means that the deformation induced by temperature plus the effects of the internal restraining force in material 1 has to be exactly the same as the deformation effects on the material 2 plus its restraining force. Right? So these are the two effects combined: temperature and restraining force. When it's all said and done, these two sides have to be exactly the same. In addition to that, because there are no other external forces acting on the system, P1 plus P2 has to equal 0. Basically, P1 will elongate the material with the lowest thermal expansion coefficient, and P2 will compress the material with the larger thermal expansion coefficient. So, but at the end, P1 and P2 must be equal to exactly the same, but in opposite directions. So P1 plus P2 equals 0, which means P2 equals to minus P1. So we need to now combine these two equations to obtain the values for the restraining force. P1 or P2, we already have stated that they have to be equal and opposite. Since we're starting from the premise that alpha 2 is greater than alpha 1, we are going to write these equations in this way. So I'm basically going to move this to this side, and I'm going to move this to that side. So we'll have P1 times L divided by A1 E1 minus P2 L A2 E2. This will be equal to alpha 2 minus alpha 1 times delta T times L. As we said before, we're operating in the condition where the temperature has already equaled out, and any kind of external temperature variation has already permeated inside, and now both materials have the same change in temperature with respect to the initial temperature. So from here, we can see if we substitute P2 equals to minus P1 into here, we basically will get P1 L A1 E1 plus P1 L A2 E2 equals to alpha 2 minus alpha 1 delta T times L. We can see from here that the L's cancel out, and if we add these two, we basically obtain P1 times A1 E1 plus A2 E2 divided by A1 E1 times A2 E2 equals to alpha 2 minus alpha 1 times delta T. And from here we can solve for the value of P1 as alpha 2 minus alpha 1 times delta T times A1 A2 E1 E2 divided by the sum. Right? This is the restraining force, the internal restraining force, which is the same, P1 and P2, right? Internal restraint. If we divide P1 by A1, then we get the stress in material 1. And if we divide it by A2, we get the stress in material 2. And basically, that's the way that you compute the internal restraining force due to the fact that these two materials are experiencing the same increase or decrease in temperature, but they have different thermal expansion coefficients. You have to be careful with these because if the thermal expansion coefficients are different enough, you might create internal stresses that could overcome the welding strength or whatever restriction mechanism you have in place to keep these two from having incompatible deformations. And so this is a very important aspect to consider when you have structures that have different materials and are subject to temperature changes.